Hello, welcome to this first video on algebraic structures. We're going to be talking about all the different structures that we work with in mathematics. What does that mean, the word structure? Well, the structure we're working in is the sort of place where we do our math. So in most of our mathematics careers, we're working with sets, and when you learn about the real numbers, then you start to learn about fields. But all these other things, groups and rings and modules and algebras, they don't really tell you about until your abstract algebra class. So I just wanted to make a few videos to clear up what these structures are. What do they mean, and what do we use them for? So let's start off with sets. You've definitely worked with sets before, but you might not be clear on what actually defines a set, like rigorously. What is a set? You've been told that a set is some kind of collection of objects, and you can assign a set a name, and you can put sets inside of sets, and so on. But this doesn't really make it clear what you're allowed to do. For example, one of the biggest paradoxes of the 20th century is Russell's paradox. So Russell's paradox goes like this. Consider, let me write this down. Consider the set of all sets. Let S be the set of all sets which do not contain themselves. So S is equal to the set of X such that X is not an element of X. Now, the question is S an element of S? Well, if S is an element of S, then it does not contain itself. Therefore, S does not contain S. You see, this follows because of the definition. If S were an S, then S would not be an S. So that's a contradiction. Okay, so what about is S not in S then? Well, if S is not in S, then by the definition of S is an S. Oh, that's bad. Okay, so we've come to a contradiction. And the way to resolve this is to set some axioms up, some rules that sets have to follow. And then if this set were constructible from those rules, then okay, well, we'd be screwed. So what we want is a set of rules. So we want rules that sets must follow. So you could have a collection of sets which do not contain themselves, but there's no way to construct a set of sets which do not contain themselves. And I'll show you what I mean. So the first rule that sets must follow is the axiom of extensionality. So the axiom of extensionality says that if two sets have the same contents, they are equal. They are in fact the same set. So for all x, for all y, So for all x and y that are sets, any z has the property that if z is in x, then z is in y, and if z is in y implies that z is in x, we must have x equals y. So let me repeat that. For all x and y, if z has the property that z is in x implies z is in y, and z is in y implies z is in x, we must have that x is equal to y. Okay, so this is visualizable. So if z is in x implies z is in y, this means that x is a subset of y. So we would have to have some kind of intersection here. And if z is in y equals, it implies that z is in x, we must have y subset x. So if two sets are subsets of each other, they've got to be equal. So x subset y and y subset x implies x equals y. So this is a useful property of sets. This allows us to prove that two sets are equal. The next property is the following. So sets have this property called the axiom of regularity. And this says that any set x which is non-empty contains as an element another set y such that x and y are disjoint. So that means that if we have some x and x is non-empty, then there's got to be some y in here such that x intersect y is empty. Okay, so we can see this as follows. For an example, the natural numbers are defined to be the set 1, 2, 3, ... Okay, what is 1? Well, if you were to go by von Neumann's prescription, von Neumann defines the number 1 to be the set containing the empty set. So this is called the von Neumann ordinal prescription. So we can see that the integers intersected with 1 as a set is definitely disjoint. Like what could this possibly be? So there's an example. Alright, and now let's go to the next axiom. So the third axiom, as Wikipedia defines it, it's an axiom schema. So this is an axiom that allows us to construct things. It's useful. So the axiom schema of specification or separation. So you are, essentially what it says is that you are allowed for any set x to construct subsets according to a rule. So if x is a set and it follows all the rules that sets have to follow, then the subset of x given by y such that some predicate upon y is satisfied and y is a element of x this is a set. So we're allowed to make up some logical statement like x is blue, x is green, x is 1, x is 2, x is less than 3. Anything like that that you can make up that follows the rules of set theory, you can construct subsets from it. So this is well defined. So a fourth axiom, this one's a lot shorter. This one's called the axiom of pairing. Okay, and it says that if x and y are sets, then the set containing x and y is also a set. So this lets us sort of slap sets together. This is really useful because it allows us to construct new sets. So, oops. There we go. If we have, for example, the set 1 and the set 2, then the set containing 1 and the set containing 2 is a set. So that's intuitive. Okay, number 5, the axiom of union. This just says that if x and y are sets, then x union y is a set, where x union y is the set of all elements p such that p is in x or p is in y. Great. That one you know all about already. Okay, another axiom that's useful is called the axiom of replacement. This basically says that if x is some set containing some elements, x1, xn, then we can always relabel the elements of the set. So we can relabel x1 and x2 and so on. So we can construct sets like green, blue, and so on. It doesn't matter what we name the elements. This is what this is saying. You can rename the elements however you want, or you can specify functions from sets to sets. So for example, a function from x to y, such that f of x is, or sorry, f of x equals y, and f inverse of y equals x, and basically x and y become the same set. If they have the same number of elements, you can basically just relabel them and they become the same set. That's why we need extra structure. The 7th axiom is the axiom of infinity. It says that the natural numbers exist. That's basically it. There's an infinite set, it's called the natural numbers, and we can do things with it. Another one that's useful, the axiom of power sets. So if x is a set, define the power set P of x, which is the set of all subsets of x. Then the power set is a set. So this is useful. Here's an example. Let's say 1, 2, 3. This is a set. Then the power set of this is, it's got the empty set in it, it's got 1 in it, it's got 2, 3, it's got 2, 3, 1 comma 3, 1 comma 2, and 1, 2, 3. So if x has n elements, then P of x has 2 to the n elements. And I'll leave that as an exercise. Great. Finally, the eighth, or hold on, how many am I at? Yeah, the ninth axiom is the axiom of choice. And this one is optional. You can do math without the axiom of choice, but it becomes different. And I'm not going to get into that because that's a heated topic. But the axiom of choice basically tells you that if you have a set X and you don't really know what's in the set with, so it's got indeterminate elements, well, you can pick an element. You can picking elements from X is allowed. So, for example, R, the real numbers. The real numbers are like a continuous line. You can't really just, pick an element. You could pick 2, you could pick 3, but like that's not very nice. If I just wanted to pick an element out of R, could I do that? According to the axiom of choice, I can. I can pick one element out of R, and I can call it x naught, and it will be a representative of R. But because R is a continuum, you need the axiom of choice to be able to do this. And the reasons are kind of complicated, but yeah, that's something that people in set theory study a lot. Okay, that covers sets. Next time I'll do groups, and then I'll do rings and fields and modules and algebras. Thanks for watching.